Have you ever wondered how AI could help scientists analyze complex images, like microscopic views of materials or 3D scans of crystals, but struggled because the data doesn't fit traditional AI tools? Today, we're diving into a breakthrough that's changing the game. Zeneses, a new platform that makes AI accessible for scientific imaging, even when the data is messy or unconventional. Let's start with the problem. Most AI models, like the ones that recognize cats in photos or segment objects in videos, are trained on natural images. Think landscapes, people, everyday scenes. But scientific data, it's a different world. Imagine trying to analyze a 3D scan of a catalyst material, where the images are super high resolution, have strange pixel formats, or are full of noise. These non-AI-ready datasets are like a puzzle with missing pieces. Traditional AI tools just can't handle them. That's where Zeneses steps in. This platform is designed to bridge that gap. It uses zero-shot learning, which means the AI doesn't need to be trained specifically on your dataset. Instead, it leverages existing models like SAM, segment anything model, and DINO, but with a twist: multi-modal adaptation techniques. Think of it as teaching a smart assistant to navigate a new city without a map, using clues from different sources to get the job done. Here's how it works. Zeneses takes raw scientific data, like FIB-SEM images of catalysts, and transforms it into a format AI can understand. But it doesn't stop there. The platform includes human-in-the-loop refinement, letting scientists tweak AI results in real time. For example, if the AI misidentifies a region, a researcher can draw a box or add a text prompt to guide it. It's like having a collaborative partner that learns from your input. The results? Impressive. When tested on challenging scientific datasets, Zeneses outperformed traditional methods like Otsu thresholding, a basic image analysis technique, and even standalone AI models. For amorphous catalyst samples, it achieved 94.7% accuracy and a 92.3% dice score, a measure of segmentation overlap. For crystalline samples, the numbers were even better, 98.7% accuracy. These aren't just numbers. They mean scientists can now analyze complex data faster and with fewer errors. But why does this matter? Many scientific fields, from materials science to astronomy, rely on imaging techniques that produce data too unique for standard AI tools. Zeneses democratizes access to AI, letting researchers focus on discovery instead of data wrangling. It's not just about automation. It's about empowering experts to leverage cutting-edge technology without needing a computer vision PhD. So the next time you see a scientific image in a paper or a lab, remember, tools like Zeneses are making it possible for AI to unlock insights that were once hidden in the noise. Science is getting a powerful new ally, and the future of discovery just got a lot brighter. Imagine a world where clean energy is more efficient, cheaper, and widely available. At the heart of this future are tiny but mighty materials called catalysts, which drive chemical reactions in devices like water electrolyzers. These catalysts need a special, helper material called an ionomer to function properly. Think of it as the conductor in an orchestra, making sure protons move smoothly and reactions happen efficiently. But here's the problem. Understanding how these materials are arranged at the microscopic level is like trying to see a crowded room through a foggy window. This dataset is all about solving that puzzle. Researchers used a cutting-edge technique called FIB-SEM, focused ion beam scanning electron microscopy, to capture ultra-high-resolution images of these catalyst layers. Why? Because traditional microscopes struggle with sensitive materials, but FIB-SEM lets scientists see details as small as a single atom. The images reveal fascinating structures, needle-like crystals of iridium oxide, O2, that have a much larger surface area than their amorphous counterparts, which could mean better performance in energy devices. But here's the catch. These images are noisy, blurry, and hard to interpret. Think of trying to distinguish between two similar colors in a poorly lit room. Traditional methods like Otsu thresholding, a basic image analysis tool, and even advanced models like SAM, segment anything, fail to accurately separate materials, especially in complex structures. That's where Zeneses steps in, a new AI-powered tool that combines the best of two worlds. Zeneses uses a clever approach called text-guided segmentation. Imagine telling a robot, find the iridium oxide structures in this image, and it does it with superhuman precision. By integrating GroundedDINO, which understands text prompts with SAM, a powerful segmentation model, Zeneses achieves accuracy scores over 90%, a huge leap from the 50% or lower seen with older methods. For crystalline materials, which are notoriously tricky due to their uniform appearance, Zeneses shines, achieving 86% accuracy in identifying key features. To put this in perspective, if you were trying to sort a pile of mixed puzzle pieces, Zeneses would be the person who not only finds the right pieces but also knows exactly where they fit. This matters because better segmentation means scientists can design catalysts with precise control over their structure, leading to more efficient water splitting and, ultimately, cheaper hydrogen fuel. This research isn't just about better images. It's about accelerating the development of next-generation energy technologies. By making complex scientific data more accessible, tools like Zeneses are paving the way for breakthroughs that could reshape how we generate and store energy. But Zeneses is just one piece of a larger puzzle. In the field of AI-driven imaging, researchers are also pushing boundaries with models like GroundedDINO. which combines visual detection with textual understanding to generalize to unseen objects. And then there's the segment anything family, which aims to be the Swiss Army knife of image analysis, segmenting any object in an image, from lung nodules in CT scans to cars in street photos. These models rely on techniques like zero-shot learning and multi-modal adaptation, where AI systems learn to interpret data across different formats, like text, images, and sensor readings. For example, FIB-SEM extends this capability to videos, while faster segment anything optimizes the technology for mobile devices. The result? Tools that are not only powerful, but also adaptable to real-world constraints. What's fascinating is how these advancements are reshaping medicine. Papers like Segment Anything in Medical Images show how these models can automate tedious tasks, freeing up doctors to focus on complex cases. And with techniques like text prompts or interactive corrections, the models become more intuitive, almost like having a smart assistant that understands your goals. So why does this matter? These tools aren't just about flashy tech, they're about solving real problems. From faster diagnostics to personalized treatments, the ability to see and analyze images with AI is opening doors we couldn't imagine a few years ago. Stay tuned for more deep dives into how AI is transforming science and healthcare, because the future of imaging is anything but ordinary. Thanks for watching, and let me know your thoughts in the comments.